So in problem 1 of the free response question, they give us this table where it says a customer at a gas station is pumping gasoline into a gas tank, and the rate of flow of the gasoline is modeled by a differentiable function f, where f is measured in gallons per second and t is measured in seconds since pumping began. Now the table gives us selected values. Part A says using correct units, so that right there is a tell for us to remind us that our answer needs to have units in there. So hopefully I'll remember that. We want to interpret the meaning of from 60 to 135 f of t in the context of the problem, and then use a right Riemann sum with 3 subintervals to approximate the value of this. All right. So what I'm going to do is I'm actually going to find this value first, and then I'm going to write the interpretation of it. So our first interval is from 60 to 90, and we are using a right Riemann sum. So for 60 to 90, we're going to use the value of 0.15, and that interval is 30 units wide, so it's going to be times 30. For 19 to 120, the right value is 0.1 times 30. And then 120 to 135, the right value for this is 0.05 times 15. So when we multiply, 0.15 times 3 gives us 0.45. 0.1 times 3 gives us 0.3. And then 0.05 times 15 gives us 0.75. So, whoops, I think I made a mistake. Yes, I did. 0.15 times 30. There we go. I missed a decimal point. So that should be 4.5, this should be 3, and that should be 0.75. So 4.5 plus 3 plus 0.75 is 8.25. So now that we have this, now we can interpret this using correct units. And so this represents the overall change. And so this represents the amount of gas pumped from 60 to 135 seconds is 8.25 gallons. And remember, it says to use units, and there it is. So I've remembered to include my unit. Now part B says, must there exist a value for C on this interval 60 to 120 such that f prime of C equals 0? So when we ask, must a certain value exist that has a given slope, this is mean value theorem. Now mean value theorem only applies with a differentiable function. And thankfully, they tell us that we have a differentiable function f. And they don't qualify it by any intervals, which means f is differentiable everywhere. And so since f is differentiable everywhere, that means it's continuous everywhere. Now odds are, it probably would be a good idea to mention that. Now this may be overkill, and if so, that's fine. But f is differentiable and thus also continuous on 60 to 120. Now it only has to be differentiable on the open interval, but it has to be continuous on the closed interval. Now since it's differentiable everywhere, we're safe for that. Now the question is, well, must there be a slope of an average rate of change of 0 to make this instantaneous rate of change? So we find the average rate of change, so f of 60 minus f of 120 all over 60 minus 120. So f of 60 is 0.1, f of 120 is 0.1. So that right there means that this is our average rate of change right here. And so since it's continuous and differentiable, fitting the definition, the criteria for mean value theorem, if this is our average rate of change, mean value theorem says that yes, there must be some point on this interval where the instantaneous rate of change equals the average rate of change. So to justify it, so by mean value theorem, there must exist a C such that $60 is less than C, which is less than 120, and F prime of C equals 0. Now you want to be sure that you show your work in finding the average rate of change using the difference quotient. Part C. The rate of flow of gasoline can be modeled by this function g of t. Using this model, find the average rate of flow of gasoline. Now, this function right here gives us the rate of flow of gasoline, and we want the average rate of flow of gasoline. So what this is saying is that we want the average value of g of t on the interval 0 less than or equal to t less than or equal to 150. So we write our integral 1 over 150, the integral from 0 to 150, g of t dt. All right, so I have the function stored right here on my calculator, and it is in radian mode. So we have 1 over 150 times the integral from 0 to 150, and that's stored in y1. And so we get 0.096. Now, it doesn't say anything about units, but we might as well be careful. And then this is 0.96 gallons. And so it says show the setup for your calculation. So we have to show what we type into our calculator. And so we have to show this right here. Part D. Use the model G to find the value of G prime of 140. So I'm going to use n deriv. And we have y1, and the value we have is 140. So g prime of 140 is negative 0.005. And we want to interpret the meaning of our answer in the context of the problem. All right. So at t equals 140. Now g prime is the rate of change of g, and g is an approximation for F, which is the rate at which gasoline is the rate of flow of gasoline. So that means at t equals 140, the rate of flow of gasoline is, now this is negative, so that means it is decreasing at a rate of 0.005. Now, G and F were in gallons per second. But now this is the rate, that rate is changing per second again. Now, some people will say gallons per second per second. Some of you who take physics will prefer gallons per second squared. And some of you may have written it like this, gallons per second like that. But all of those give the interpretation of what this tells us. Thanks for watching, and we'll see you in the next problem.